Today we're going to look at a bit of one of my favorite subjects in mathematics, and that is the study of integer partitions. But what is an integer partition? Well, let's look at the definition. So lambda, which is a k tuple, lambda 1, lambda 2, up to lambda k, is called an integer partition of n if lambda 1 is bigger than or equal to lambda 2, which is bigger than or equal to lambda 3, and so on and so forth. They are all bigger than or equal to 1, and most importantly, lambda 1 plus lambda 2 all the way up to lambda k is equal to n. And so we'll also want the following definition, which is the partition function, and that is p of n, and what it gives you is the number of partitions of n. Okay, so let's look at some examples. So we would say that p of 0 is equal to 1, and that is built out of just the empty partition. And then p of 1 is 1 because we have the single partition, which is just a single 1. And then p of 2 is 2 because we have the partition that is just a single 2 and then a 1 and a 1. Oh, and by the way, often when we write a partition, we'll just write it as the addition problem. So here we would write the partitions of 2 as 2 and 1 plus 1. And then p of 3 is 3 because we've got 3, 2 plus 1, 1 plus 1 plus 1. P of 4 is 5. As you can see, we've got them over here. P of 5 is 7. We've got them right here. And then, well, it just gets bigger and bigger and bigger. And this actually grows quite fast. So now you might ask, well, we've got this P of n function. Is there a closed form for P of n? Well, there sort of is. And so most recently, the most closed form is due to Ken Ono and Amanda Folsom. But maybe a more famous and older version, which is not quite a closed form, it's written in terms of an infinite series, is due to Rademacher. And it can be written as the following expression. So notice there's a lot going on here. So we've got p of n is equal to 1 over pi times the square root of 2. That's already kind of crazy. And then the sum as k goes from 1 to infinity of a sub kn, the square root of k, the derivative with respect to n of 1 over the square root of n minus 1 over 24, and so on and so forth. Notice we've got this hyperbolic sine term in there. But notice that we have to define a sub k of n, and it's defined like this. So it's going to be the sum over all m between 0 and k, where the GCD of m with k is 1, so they're relatively prime. And then we've got e to the I pi smk minus 2mn over k. But then we need to define smk. So smk is 1 over 4k, and then the sum as j goes from 0 to k minus 1 of the cotangent of pi j over k times the cotangent of pi mj over k. So as you can see, this is, really a crazy formula in my opinion, and it would be probably pretty hard to work with. So you might say, is there a better tool for counting the number of partitions of n so that we can prove things about them? And yes, there is, and that's using something called a generating function. So let's look at that. So a generating function for a sequence is a formal power series where the coefficients of maybe q to the n, if we're letting q be our formal variable, are the nth term of the sequence. So if our sequence is the number of partitions of n, that would be the sum as n goes from 0 to infinity of p of n times q to the n. We're using q as that's kind of traditional in the study of integer partitions. And this may look kind of gnarly, but we've got p of q here and p of n here. So we consider those as being different types of functions. One is the generating function and one is the sequence. And we just use context to see which one we're talking about. Okay, so the nice thing about this is we can get a nice formula for the generating function. So let's do that. So I'm going to start with my p of q right here. And then, well, let's recall it's this over here, but I'm going to write the expansion of the first several terms. So notice we'll have 1 plus q to the 1. I'm going to put the exponents even if there are just ones there, because we'll see that we essentially express the partitions inside of the exponents. And then we'll have plus 2q squared, because remember there are two partitions of 2, but I'm going to write that as plus q to the 2 plus q to the 1 plus 1. So notice I just took the partitions and I put them in the exponents. And then I'm going to continue doing that kind of thing. So q cubed plus q to the 2 plus 1 plus q to the 1 plus 1 plus 1. And then for 4, I have q to the 4 plus q to the 3 plus 1 plus q to the 2 plus 2, and then plus q to the, let's see, 2 plus 1 plus 1, and then q to the 1 plus 1 plus 1 plus 1, and then so on and so forth. So notice this encodes exactly what we want it to. We've got exactly a single partition of 1. These are both q squared, so we've got 2q squared. These 3 are q cubed. We've got 3 of those, and then we've got 5q to the 4th, and so on and so forth. But this motivates us to perhaps factor this or see some sort of factorization. So let's observe that we can factor out a 1 plus q plus q to the 1 plus 1 plus q to the 1 plus 1 plus 1 plus so on and so forth. So that would be like factoring, let's see, q to the 1 right here, and then q to the 1 plus 1 from this term, a q to the 1 from this term, a q to the 1 from this term because there's a single 1, a q to the 1 plus 1 from this term, and then as you can see it kind of continues on. But then we can factor multiples of q squared as well. So let's see, we've got 1 plus q squared plus q to the 2 plus 2 plus q to the 2 plus 2 plus 2, and so on and so forth. So then we can just keep going. So we'll have like 1 plus q cubed plus so on and so forth. It'll be q to the 3 plus 2, 3 plus 3, q to the 3 plus 3 plus 3, and so on and so forth. So let's, for example, see how this works. Let's say we wanted to achieve this term right here, this q to the 3 plus 1. Well, we would do that by multiplying out this q cubed, this number 1 here, and then this q to the 1 here. Maybe I'll put a q to the 1 here just so that it's super clear. And then for all of the terms in the product that I haven't written, because this obviously keeps going on and on and on, for like our q to the 4th, our q to the 5th, so on and so forth, we just choose 1. Okay, so I think that's shaping up. Now let's see what we would do for this q to the 2 plus 1 plus 1 term. So we would take a 1 from here because there's no 3's. We would take a q squared from here, and then we would take a q to the 1 plus 1 from here. Okay, so needless to say, I think even though we haven't done it super carefully, we've motivated that the partition function p of q, the generating function, can be written as this infinite product. But if you look closely, each term in this infinite product is a geometric series, so we might as well sum it up. So this first term sums up to 1 over 1 minus q. This second one to 1 over 1 minus q squared. The third one to 1 over 1 minus q cubed, and so on and so forth. So we could finish writing this as the product as m goes from 1 to infinity of 1 over 1 minus q to the m. And now I'd like to observe some stuff right here. We can read off exactly the control of this generating function over the types of partitions. So this term right here is controlling the parts of the partition that are equal to 1. This term right here is controlling the parts of the partition that are equal to 2. I guess I haven't carefully proven what a part of a partition is, but one of these lambda i's is a part of our partition lambda. So for instance, if we go over here and look at perhaps 4, 3, 2, 2, 1, which is a partition of, let's see, 11, notice it's got a part equal to 4, a part equal to 3, 2 parts equal to 2, and 1 part equal to 1. So that's how we would say that. Okay, and then this one right here controls the parts equal to 3, and then so on and so forth. And then if we go up here to the expanded version, let's observe that this number 1 in this expansion deals with 0 parts equal to 1. And that's because any partition that has a 1 in it will have a product from either this q to the 1 if there's 1, 1, this q to the 1 plus 1 if there's 2 1s, and so on and so forth. And then, well, now we can just go down the line. So this is one of the parts are equal to 1. This next one is 2 of the parts are equal to 1. This next one is 3 of the parts are equal to 1, and so on and so forth. And then, well, we can do the same kind of thing over here. So this number 1 here means that there are 0 parts equal to 2. This number, this q squared here, means that there's 1 part equal to 2. This q to the 2 plus 2 means that there are 2 parts equal to 2, and so on and so forth. So the product, or sorry, the sum as a whole, which turns into the summed up geometric series, controls which types of parts you're using. And then how far you go in the series controls how many times you're using each part. Okay, so now let's use this observation that we've just made to prove some theorems about integer partitions. Now we're going to prove a really classic theorem, which I think was first proven by Euler, and that is the number of partitions of n using only odd parts equals the number of partitions of n with distinct. And by distinct, I mean unrepeated parts. So that means the parts can be used either 0 times or 1 time. So let's go over here to a bit of an exploration with n equals 7 to get some motivation for this. So the partitions of 7 using odd parts are 7, 5 plus 1 plus 1, 3 plus 1 plus 1 plus 1 plus 1, and then the sum of 7 ones. So notice there are 4 partitions of n using odd parts. But what about distinct parts? Well, we've got 7, 6 plus 1, 5 plus 2, 4 plus 3, and then that's it. Notice if we try to have anything else, for example, if we try to use 3 as the largest part, then the leftover bit would be 4. But any partition of 4 would be like 3 plus 1. We can't use 3 again. 2 plus 2, but then we use 2 twice. And so on and so forth. We will not have distinct parts. Okay, so anyway, now let's look at the proof of this theorem, which will use generating functions. So let's start with the generating function for partitions of n into distinct parts. So I'll write that as the sum as n goes from 0 up to infinity of p distinct, I'll put just dist for distinct, of n times q to the n. And so let's see, I think from some things that we saw while we were exploring the generating function for all partitions, we can kind of just write this down. So let's observe that it's going to be 1 plus q times 1 plus q squared times 1 plus q cubed, and so on and so forth. So let's recall that written as the product of infinite series, where you were in those infinite series controlled how many times you used each part. So this 1 here means we're using 1 0 times, 1 1 time. 2 0 times, 2 1 time. 3 0 times, 3 1 time, and so on and so forth. So we're only allowed to use each type or each part of the partition exactly 0 times or 1 time. Okay, nice. So now what I'll do is I'll rewrite this, but I'll spread it out a little bit. So let's write this as 1 plus q times something. I'll just put a line there, I'll fill it in a bit. And then 1 plus q squared times something. Again, I'll just write a line there. I'm going to fill it in just a bit. 1 plus q cubed times something. 1 plus q to the 4th times something, and so on and so forth. But now what I'll do is I'll multiply here by 1 minus q over 1 minus q. Here I'll multiply by 1 minus q squared over 1 minus q squared. Here I'll multiply 1 minus q cubed over 1 minus q cubed. And then here I'll multiply 1 minus q to the fourth over 1 minus q to the fourth. And then I'll keep going on with that kind of pattern. And then let's put parentheses up here in the numerator just so it's kind of clear what's going on. Okay, so now let's make that product. So notice if we take the product of these first two, we'll get 1 minus q squared. These second two will get 1 minus q to the fourth. These will give us 1 minus q to the sixth. These will give us 1 minus q to the 8. So let's see, in the end, we'll have this product 1 minus q squared, 1 minus q to the 4, 1 minus q to the 6, so on and so forth, all the even type terms in the numerator. But notice in the denominator, we've got all the terms, 1 minus q squared, 1 minus q cubed, 1 minus q to the fourth, and so on and so forth. But let's observe that we get some obvious cancellation. This 1 minus q squared cancels this 1 minus q squared. This 1 minus q to the fourth cancels this 1 minus q to the fourth. There's a 1 minus q to the sixth that gets canceled by something in the denominator as well. And observe that in the end, we're simply left with 1 over 1 minus q times 1 over 1 minus q cubed times 1 over 1 minus q to the fifth. But recall, writing it like this is expressing it with only using parts equal to 1, that's controlled by this term right here. Parts equal to 3, controlled by this term right here. Parts equal to 5, and so on and so forth. All that's left is the term that controls the parts equal to an odd number. So that means here we could write this as the sum as n goes from 0 up to infinity of p sub odd of n times q to the n. But now, since these two power series are equal, that means all of the coefficients are equal. So that means p distinct n is equal to p odd n as desired. Okay, so now let's see how far this kind of argument can take us. Okay, so now let's do a bit of exploration. So on the last board, we proved that 1 plus q times 1 plus q squared times 1 plus q cubed was equal to this infinite product 1 over 1 minus q times 1 over 1 minus q cubed, and so on and so forth. Now that was, of course, to prove something about integer partitions, but let's see if we can develop something similar and then extract something about integer partitions out of it. So I think a logical thing to do would be to, instead of stopping at the first term here, stop at the second term, or more generally the nth term. But we'll just do the second term, and then I'll leave it to you as a little bit of a homework exercise to see how far you can push it. So here I'll just say we're going to explore a bit. So let's look at 1 plus q squared, and then 1 plus q squared plus q to the fourth, and then 1 plus q cubed plus q to the sixth, so on and so forth. So now we're going to do the same thing. We're going to squeeze in a 1 in between each of these parts. But now what 1 are we going to squeeze in? Well, let's multiply here by 1 minus q over 1 minus q. So I'll just write it like that as we're multiplying by that version of 1. And then here in the next part, we'll multiply by 1 minus q squared over 1 minus q squared. And then in the next part, we'll multiply by 1 minus q cubed over 1 minus q cubed. But if we multiply from the left to the right, and by that I mean we're going to multiply this term right here into this term right here, this 1 plus q squared plus q to the fourth into the 1 minus q squared, and then so on and so forth, you see that we get some nice simplification. So let's see, multiplying these first two will give us 1 minus q cubed. And then in the denominator we have 1 minus q. And then multiplying the second two will give us 1 minus q to the 6 over 1 minus q squared. Then the next one will give us 1 minus q to the 9 over 1 minus q cubed. So I think we can write down what the next one would be. That'll be 1 minus q to the 12 over 1 minus q to the 4, and then 1 minus q to the 15 over 1 minus q to the 5, and then I'm going to write one more, 1 minus q to the 6 over 18 over 1 minus q to the 6. And then that just continues going on and on and on. But we get some cancellation just like we did in the simple case, if you will. Notice that this 1 minus q cubed cancels this 1 minus q cubed. Then notice that this 1 minus q to the 6 cancels this 1 minus q to the 6. And then as you can maybe see, the 1 minus q to the 9 will get canceled with something over here. And then the 1 minus q to the 12 will get canceled with something over here as well. In fact, everything in the numerator will get canceled. And what will we be left with? So we're going to be left with 1 over 1 minus q times 1 minus q squared times 1 over 1 minus q to the 4th times 1 minus q to the 5th times 1 over 1 minus q to the 7th times 1 minus q to the 8th, and so on and so forth. So notice what's missing here is 1 minus q to the 3 times something. Okay, so now I think we can read off what this means about partitions. So let's observe over here on this left-hand side, using the kind of observation that we did maybe much earlier in the video, this is related to the number of partitions of n where each part is used 0, 1, or 2 times. So of course, this number 1 here is like 1 being used 0 times. This term is for 1 being used once. This term is for 1 being used twice. And then that continues on and on and on. And then, well, what about the other side of the equation? Well, I think the other side of the equation is related kind of clearly to the number of partitions of n using parts not divisible by 3. Because notice we're leaving off everything of the form 1 minus 3 times something. And now this is really a parallel version of what we had before, like an extension, if you will. Notice the thing we had before could be recast as the number of partitions of n where each part is used 0 or 1 times. So 0 or 1 times is the same thing as distinct, is equal to the number of partitions of n using parts not divisible by 2. But not divisible by 2 equals odd. So now viewing it like this, each part is used 0, 1, or 2 times, and parts not divisible by 3 gives you a clearer way to see how this might be generalized. So see if you can think about the most general version of this result, and if you can prove it. Maybe post what you get in the comments, and that's a good place to stop.